Okay, this is the video lecture for Math 283 for Wednesday, September 9th. And the topic today is vectors. This is section 12.2 of the textbook. What exactly is a vector? A vector is a quantity that has both a magnitude and a direction. Vectors come up quite frequently in the physical sciences and engineering. And there are many quantities where we want to know both a magnitude and a direction. Let me give an example. If you were to say you're driving at 60 miles an hour, that would be a scalar quantity, which is not a vector. But if you were to say I'm driving 60 miles an hour due east, that would be a vector quantity because you've specified both a magnitude and a direction. And typically we represent vectors with either a bold-faced letter, but because I can't illustrate bold-faced when I'm writing on a whiteboard, the other thing I can do is I can represent a vector with an arrow above the vector. So this indicates a vector. And graphically, we typically would represent a vector as a line with an arrow, okay? And the direction of our vector is indicated by the direction of this arrow. And the magnitude is related to the length of the vector. Okay, so the longer the vector is, the bigger the magnitude of the vector, and the arrow tells you your direction. Now, one critical point with vectors is we can take this vector, and I could move this vector around on this board, and as long as I keep the direction the same and the length the same, that's the same vector. Okay, so it's not necessarily tied physically to a certain point in the board. But as long as I keep the direction and the length the same, I can move it anywhere I feel like. Let's talk about some operations we typically would perform in vectors. And one of the most basic operations is vector addition. Okay, and let's suppose we'd like to add two vectors, a vector u plus a vector v. How do we do this? Well, I'm first going to talk about how we do this graphically. So I'll draw two vectors. I'll draw a vector u like this. And then we can draw a vector. Let's suppose we have another vector v that's pointed in some different direction. What I do to add these vectors is I then place v, I move v so that the tail of v touches the tip of u. So this is my vector v. Suppose that's v. Okay. So I connect these vectors in this way. It's called the tail to tip method. And then I can connect, let me actually do this in a different color. I can connect these two vectors like that, and this is vector u plus v. Okay, that's vector u plus v. Now, an important point to note here is I could have also started with the vector v, so I could have started like this. That's v. And then I could have placed the tail of u at the tip of v, so I get something like this. U. And then I could have connected the tail of v to the tip of u, like that, and I get u plus v, okay? These are both legitimate ways. There are two different ways to add vectors. Because addition is commutative, we can either start with u plus v or v plus u graphically, but we get the result. The point is we get the same end vector u plus v. Okay, so that's vector addition. Let's talk about subtraction. How do we do vector subtraction? The good news with subtraction is it's very similar to addition. What we do is if we're doing vector u minus v, what we do is we imagine that we have u, vector u, plus the negative of v. Okay, and so let me go back to our example. I can try and recall the directions I had here. I think vector u was more horizontal. So let's take vector u like this. Okay, that's u. And if you guys remember, vector v was pointed more like this. So what I'm going to do is draw on a dashed line like that, vector v. Okay. But now what I'm going to do is instead of having v, we have negative v. Now, by the way, what does it mean to have a negative vector? All it means is, like, the vector negative v has the same magnitude as a vector v, but is opposite in direction. So what I do is I flip this direction around, and V will point down like that. Okay. And now what I do is I follow the same method where I connect the tail of U to the tip of V. So I'll draw that in blue. Okay, so I draw this vector here. And this vector right here is U minus V. Okay, that may be getting a bit small there. I hope you guys can read that with the resolution of the video. But vector subtraction is very similar to vector addition. It's just that we add a minus sign on. Let's talk about scalar multiplication. And what that means is multiplying a vector by a constant. So let's consider the vector c times the vector v, okay? What does this do to multiply by a constant for a vector? It's very simple. All it means is that the vector cv has the same direction as the vector v, okay? But the magnitude or the length is c times longer, or the magnitude is c times greater. Okay. If c is less than 1, then this vector would have a length that's smaller than v. Okay. So all this c does is it changes the magnitude or length of the vector by a factor c. All right. There's other types of multiplication with vectors. That's taking the dot product and the cross product. Those operations are more complicated, and we're going to consider those in the next few days. But today we're just going to consider scalar multiplication. Again, what I'm giving you here in this video lecture is a theoretical introduction to the material. I'm not really doing any example problems. I will do example problems in the live sessions. So if you guys want more practice problems, we can do those then. Okay, let me talk about something called the position vector. And actually, I think that I'm going to erase this and start with a fresh border here. Okay, so what we're going to draw here is our 3D coordinate system, x, y, and z. Okay, I told you guys you can take a vector and you can move it around. It's the same vector as long as you keep the position and the length the same. But there are different representations of a given vector. And one particular representation is if you move a given vector so that its tail lies at the origin. That's called the position vector. Let's draw it like this. And to indicate that this vector is coming out into space, I'm going to draw some dashed lines here. This is in the xy plane. And so this could be called the position vector. And we could have a point P here. And this is the origin. Okay. And let's label this the vector A. By the way, I should have mentioned, you can, if you have 2 points in space, you can connect them with a vector. Okay. Any 2 points will create a vector. And I'll talk about how to do that with components. And I'll talk about components right now, actually. So let me talk about vector components. Okay, so another way we can think of a vector is we can break a vector, a given vector A, into components. And components are basically projections of the vector A onto the 3 respective coordinate axes. So we can think about, how much x-ness do I have in this vector A? How much y-ness do I have in this vector A? How much z-ness do I have in this vector A? For example, if you had a vector that was entirely in the xy plane, there would be no z component to that, right? So that you can think of this as a projection, components as a projection of a vector onto various coordinate axes. And the way we do this is we can represent the vector A. We can write it in component form. And we write the components, we use these special brackets here. And A1 is the x, this is the x component of our vector A. A2 is the y component of our vector A. And A3 is the z component of our vector A. What if we had 2 points? Let's say we had 2 points, and one point was represented by point A, which had which this point A has the coordinates of x1, excuse me, put that wrong, y1, z1, and point B has components x2, y2, z2. Oh, excuse me, not components. These are actual points, okay? These are not vectors. These are points in the 3D coordinate system. And then what if we created a vector v, or vector A? Let me use the symbol, I'll use the symbol A here. And let's suppose this vector A connects these 2 points. And this is how we could write it. Vector A is connecting these 2 points in space. You know, I could draw these 2 points in here. I won't do that, but let's say we just have 2 points somewhere here. How do we find the components of the vector A? Well, it turns out the components of the vector A are simply the point x2 minus x1. That's the x component, y2 minus y1, and z2 minus z1, okay? This is if you have 2 points in space. Maybe I should do an example here. Why don't I do a basic example and make up an example? Let's say we have a point, let's say point A is the point 1, minus 2, and 3, and point B is the point 3, 5, and 1, okay? So we have 2 points in space. We can create a vector connecting these 2 points, and we can then write the components here. So the vector that connects these 2 points, vector A, will have components of 3 minus 1. That's for the x component. 5 minus 2 for the y component. And finally 1 minus 3 for the z component. Okay, and simplifying this, we get 2, we get 7, right? And we get minus 2. So these are now the components of the vector A that connects these 2 points, okay? All right, let me talk about a couple more concepts related to vectors. And this has to do with calculating the magnitude of a vector. Okay, how do we calculate the magnitude of a vector from the components? So if we have a vector A, and it equals A1's components A2, A3 for the x, y, and z, the magnitude of vector A is indicated with absolute value signs. Again, the magnitude is just the length of our vector, and there's a simple formula for calculating this length. It's equal to A1 squared plus A2 squared plus A3 squared, okay? That's the magnitude of our vector. And we actually could derive this. You can derive it from doing some, if we were to plot a vector and its components on a 3D coordinate system and use the Pythagorean theorem, we could derive this formula. But I'm not going to do that. Basically what we do is we take the squares of each of the components, add them together, and take the square root. Okay, let's do a couple other operations. How do we add or subtract vectors algebraically? In other words, if I have 2 vectors, A equals A1, A2, A3, and I have another vector B, which has components B1, B2, and B3, okay. How do I, if I'm interested in the vector A plus B, okay, what is this vector in terms of components, or A plus or minus B? Well, the good news is, it's very simple. All we do is we just add or subtract the respective components. So the vector A plus B will be A plus or minus A1 plus or minus B1, A2 plus or minus B2, and A3 plus or minus B3. So these are the components of A plus or minus B. So I talked about graphically how to add or subtract 2 vectors, and now we can also talk about, algebraically. If you had the vectors by components, how would you get the sum of A plus B or the difference? And scalar multiplication is similar. You know, if you're interested in the C times A, right? In component form, this would be CA1, CA2, CA3, okay? let's consider as a final topic. I want to talk about unit vectors. So basically, what is today? I'm just giving you guys an overview of vectors. I hope you guys have seen this before. If you've taken a physics class, you may have dealt with vectors, or an engineering class. So some of this may be familiar to you guys. We're just looking at it from a mathematical standpoint. I'm not going to talk about any applications, although there are many applications of vectors. Let me talk about the unit vector. The unit vector, or a unit vector, is a vector with a magnitude of 1. And if I have a vector A, okay, which may not have a length of 1, it may have a longer or shorter length, how do I find the unit vector for vector A? Well, the unit vector is represented with u here. And the way we do this is we take vector A and we divide by the magnitude of vector A. And that will give us a unit vector, okay? So the unit vector here is pointing in the same direction as A, but its magnitude is 1 because we're dividing out the magnitude of A. So that's what a unit vector is. And unit vectors are useful in describing a basis. So let me just talk about the basis vectors. Okay, basis vectors are unit vectors along the x, y, and z axes, okay? And typically these vectors are represented with the letters I, J, K. So if I were to draw a 3D coordinate system here, this is x, y, z. The basis vectors point along these axes. I is for x, j is for y, and finally k is for z, okay? These unit vectors, these basis vectors, point along the respective axes but have a length or magnitude of 1. So in terms of components, I can write the vector I, the basis vector I, as being equal to 1, 0, 0. The vector j as being equal to 0, 1, 0 in terms of components, and the vector k as being equal to 0, 0, 1. Okay? These are the basis vectors, and very frequently we will write a vector in terms of its basis vectors. I would say that's the most common way to write a vector. Not in terms of components. Typically, people would not necessarily draw a vector, although you could, but a very common way to express any vector A. And so any vector A can be written, now remember this is A1, A2, A3. I can write this in terms of its bases as A1, the component A1, times the vector I, okay, plus A2 times the vector J, the basis vector J, plus A3 times the basis vector K. So I can write any vector in terms of its basis vectors. Okay, this concludes this whirlwind review or overview of vectors. In tomorrow's class, I will do some practice problems with you guys involving vectors, and then we'll go over some of the homework problems for that homework that is due. And then on Thursday and Friday, we'll talk about the 2 ways you can multiply vectors together, that being the dot product and the curl. Okay, I'll see you guys tomorrow.